This is the shell method. This is another way to find volumes of these volumes of surfaces of revolution. Or volumes of revolution, I guess is what they're called. Shell method. Okay. So the way this one works is, suppose now I were to ask you to take that same, well, in fact, let's just do this first example as our motivator here. Example one says find the volume of the revolution, the volume of the solid of revolution formed by revolving the region bounded by y equals x minus x squared about, and the y-axis about the, sorry, and the x-axis about the y-axis. Okay, so we're going to now revolve this around the y-axis. Now, before we do that, let's note that we can factor an x out of here, and that leaves us with x, or sorry, 1 minus x on the inside of the parentheses there. And so that tells us that we have intercepts at 0 and 1. If you set that equal to 0 and solve, you get x equals 0, you get x equals 1. This is a parabola opening down, so it's going to be something like this. Now, we've already seen that if we wanted to revolve this thing around the x-axis, that would be a disk method type of problem. Here, now we're taking this and revolving it around the y-axis, so this way, horizontally kind of, or we're revolving it sort of in a horizontal direction, but around a vertical axis. Okay, so now if you think about maybe using the disk method here, we would have to use horizontal rectangles to make that happen. And that would be a pain because this is what the rectangle would look like. And in order to do that, this would have width delta y. And so everything would have to be written in terms of y. And that would mean we'd have to come up here and solve this equation for x equals f of y. That would be pretty hard to do because the right side is a quadratic and it would be really messy. In fact, we'd get two square root functions and we'd have to like go from the right square root function to the left one, and yeah, it would be a real mess, and the integrals themselves would be very difficult to do. So the disk method here is not ideal at all. So instead, we have this other method that we call the shell method. And the shell method, we're going to now use vertical rectangles. And think about now what just this rectangle would look like if just it were revolved around the y-axis. Kind of hard to draw these things very accurately, but try to picture what's happening here. Then it would go back in the board right there, and it would continue on around all the way. Basically, we get this type of drawing here for this situation. Everybody kind of see what that is? It's like I'll make this a little bit more solid here. See what that shape is? Kind of like a thin shell. In fact, that's why they call this the shell method. And the inner one would go around like that. The outer one there. Yeah, it's not too bad of a drawing, I think. So you kind of see what happens when you just revolve that rectangle around the y-axis. You get that kind of a thin shell. Now, picture what would happen if I had a different rectangle in a different place and I revolve that. Then I get another shell, right? And basically, if you could picture a whole bunch of these sort of starting at x equals 0 and ending at x equals 1, you would get a whole bunch of these little shells sort of stacked right next to each other. And you could then find the volumes of each of those separately. Assuming you could find the volumes of each of them separately, then you could add them all together, and that would give you an approximation to the volume, the total volume. And then you could take the limit and go to infinity, and that would give you the exact volume. So the question really then becomes, what the heck is the volume of that shell? What is the volume of the shell? Okay, so that's what we'll do first here. So imagine what's the best way to figure out what this volume is here. Well, suppose that we were to cut that ring right there, that shell right there. So you would cut the thing right vertically right there, slice it, and then take it and lay it out. Okay. So if you did that, if you cut it and then laid it out flat, what kind of shape would you get? You get something that looks like this, and that's like a three-dimensional rectangular solid, basically. So let's identify the dimensions of this thing. So the width of it, that right there, according to what we have drawn on the original drawing there on the left, that is going to be delta x. The height of it from here to here, that's just going to be the function itself, but we're going to actually call that h of x. And in this case, h of x is actually just the function itself. It's just from the x-axis up to the function, right? But in this case, it is f of x, although that's not always going to be the case, as we'll see. So that's why we call it something else. And then finally, the other one that we have here is, we call it, well, that's the circumference, basically. So I'm just going to call that L for now. Does everybody see that that really is the circumference of that shell? Because when you cut it and lay it out flat, well, then that what was the circle now is the length of the rectangular solid there. So what is L? Well, according to our geometry formula, since that's the circumference, it's 2 pi times x, because the distance from here, from the y-axis to that rectangle, that's what we're going to call, in fact, we usually call that p of x, but in this case, p of x is just x. I'm going to call it p of x here too, though. So p of x, in this case, here, p of x equals x. But that's not always true. P of x could be something besides just x. It's to define what p of x actually is, you can just say it's the distance from the axis of revolution to the representative rectangle. And since here the distance is just, well, the axis of revolution is the y-axis itself, we're just simply going from the y-axis to the rectangle. That's just the distance of x. Okay, and we'll see somewhere it's not just x, and you'll see what I'm talking about in further examples. Anyway, so if you put all this together here, what is the volume of this solid? Well, the volume of a rectangular solid is length times width times height, right? So the length we said was 2 pi p of x. So 2 pi p of x. The height, length of width times height, is h of x. And then the width we said was delta x. Okay, so that's the volume of a single shell there. And if you then do all of the rest of the steps to get to the integral, that is, take the summation of that, and then take the limit as the number of shells goes to infinity. That gets you your definite integral, but basically you can just pick that all up from the volume of a single shell and get the formula for the shell method. And so that's 2 pi times the integral from a to b of p of x, h of x, dx. And so that is the shell method formula. And so really the goal on these shell method problems, well, also on the other ones, is you want to just identify what are the pieces that you need to plug into that formula. Well, in this case, what do we need? We need p of x and we need h of x. And the other ones, the disk method and the washer method, what were we trying to find? We were trying to find r of x, right? And sometimes if it was the washer method, big R of x, and then also small r of x. So here we need to find both p of x and h of x. Any questions about the derivation of this shell method formula? Everybody kind of see how that's working. It's a bit confusing. It's a bit more bit more complicated than the disk and the washer method, but if you think about it, it makes sense how we figured that out. Any questions on that? Okay, if not, then let's do that first problem. I'm going to go ahead and clear this out and write it again. So for that first problem, we wanted to find the volume of the solid revolution formed by revolving this region bounded by this function, y equals x minus x squared, and the x-axis about the y-axis. And we noted that this was equal to this. And so this was the situation we had for this function. That was 1, the other one was 0. Representative rectangle looks like that. And that forms a shell when it's revolved around the y-axis. And then you can kind of picture maybe what that whole thing would look like if you revolved that entire region, that parabola opening downward, bounded below by the x-axis. You can picture what that would look like if the entire thing were revolved around the x-axis, sorry, the y-axis. It would look, I don't know if you've probably seen those things in like science museums where you put a coin in it and it sort of slowly spirals down into the hole at the bottom. Kind of like that, maybe. I don't know, but something like that where you could maybe drop a penny in there and have it spiral down. Anyway, just to get a picture of what it looks like. So again, what we need to identify here is what is P of x and what is H of x. Since we are only revolving around the y-axis and not some other vertical axis, P of x is just equal to x. And out further here, so P of x equals x. H of x in this case is the function itself, because again, it's the rectangle starts on the x-axis and ends on the top of it is on the function itself. So here H of x is equal to x minus x squared. So that's really all we need to just plug these into the shell method formula. We get 2 pi times the integral from 0 to 1. P of x was x. H of x was x minus x squared. So there we go. That's the integral we have to find now. That integral itself is actually not that difficult. Again, comparing that to what we would have had to do trying to do the washer method on this is very much easier. Now we just have to find our antiderivatives here. 1/3 x cubed minus 1/4 x to the 4th. Evaluated from 0 to 1 again, nicely. 2 pi 1/3 minus 1/4. And then that's going to be, what is that? 4 pi over 12 minus 3 pi over 12. So pi over 12. Multiply that by 2, you get pi over 6, I think, at the end of all this. So that then will be the volume of that solid of revolution around the y-axis. Any questions about that one? Okay. If not, let's go ahead and try a different one. I'm going to go ahead and skip example 2 because it's pretty simple. It's not really illustrative of what we're trying to do here, and plus I want to save a little bit of time. So let's move on to the next one. Example 3. So this is a good one because it's going to show, in both situations, it's going to show why sometimes the P of x is not just x, and sometimes the H of x is not just the function itself. So example 3 says, find the volume of the solid formed by revolving the region bounded by the graphs of this 4th degree polynomial, so y equals x to the 4th. plus 2x squared plus 1, and y equals 1, and x equals 1. And we're going to revolve this about a particular line. Now, in this case, that line is not the y-axis. It's another vertical axis. X equals 2 now. Okay. So let's try to draw this thing to see what it's going to look like. So we have a fourth degree polynomial shifted up 1 unit. We're revolving this. Let's see, we're blocking it, or we're bounding it by x equals 1, and we're revolving it around this line, x equals 2. So that is where I'm going to put the axis, because that is going to be the axis of rotation. That is the thing that we are revolving the whole thing around, that axis, or axis of revolution, however you want to say it. Okay, x to the fourth plus 2x squared plus 1, and we're bounding this by, let's see, what does it say? Bounded by this graph y equals 1 and x equals 1. Okay, so y equals 1, we'll say, is right here. We're bounding it there. X equals 1, we're bounding it there as well. This is a bound, that vertical line. And then the function itself. Let's see, when we plug that function, when we plug in 0, we get 1. When we plug in 1, we get 2, 4. So the function is going to start here and end here. And it's a fourth degree polynomial, so I don't know what else it's going to do, maybe something like that. So we're bounding again by that vertical line, x equals 1, and also by this horizontal line, that's y equals 1. Everybody see kind of what this region is? Bounded by the function, the horizontal line y equals 1, the vertical line x equals 1. That whole region, all of this, is now going to be revolved all the way around. So like if you were to revolve it that far, what you would see then is it would come back into the board here somewhere. You just kind of see a mirror image of it over here. That's just a cross section. Of course, then it just continues to go around like that. So it's kind of like a big, I don't know, volcano maybe is the kind of what it looks like, with a huge caldera in the middle of it. I'm just trying to picture what the three-dimensional solid is going to look like. Everybody get that picture? Stop me if anything is not clear. So now what we want to picture here, using the shell method, if I were to take one representative rectangle, that would be it. And then again, if you were to picture what that representative rectangle just by itself would look like, that would be the shell as it revolves all the way around that line, x equals 2. All right, now let's start to identify the pieces of this. The height, h of x of this thing, is this vertical distance here, and that's h of x. Notice that h of x is not the function itself. The function itself would be going from here up to that, up to there, right? Let me draw that a little bit better. It would look like this. That would be the function itself if the rectangle went all the way down to the x-axis. But it's not going all the way down to the x-axis. It's stopping right there, right at 1, at y equals 1. So the bottom of it is at 1, and the top of it is lying on the function itself. So what is h of x then? Well, h of x would have to be the function minus 1. So x to the fourth plus 2x squared plus 1 minus 1. And again, the reason we're subtracting off 1 is because we have to take off this vertical distance right here, because that is not part of the rectangle. And that height right there is in fact just 1. Everybody see that? So if we simplify that, that becomes x to the fourth plus 2x squared. And the 1's cancel nicely, so we just get that. Okay, now the next thing we need to figure out is what is the p of x? P of x is the distance, like I said before, it's the distance from the axis of revolution or axis of rotation to the representative rectangle. Now, this distance here from the y-axis all the way to that axis right there, what is that distance? Well, that's 2, right? That's the horizontal distance of 2, right? That's the whole thing. So like if p of x were just y-axis to that 2, then it would just simply be 2. However, for us, it's the representative rectangle is right there. So we actually need to take off this part, this much. We got to take off this much. So it's 2 minus this much. What is that much? That's just x, because remember that the distance from the y-axis to the rectangle itself is x. Okay, so that's just x. So what are we going to do? We need this distance. And that has to be then 2 minus x. So that's telling us then that p of x is equal to 2 minus x. Is this clear? What's happening? How we found p of x? Basically, it's kind of a quicker way to do this is just to say, okay, well, the axis of revolution was not the y-axis. Okay? So whatever it is, it's going to be that number minus x. Provided, of course, that the region that we're talking about is to the left of that axis. If it happened to be to the right, then it would be x minus 2. Anyway, so there we go. We've identified both of this. And so now um, we can plug this stuff into the formula. So the volume of the whole thing is going to be 2 pi integral from 0 to 1 p of x, 2 minus x, h of x, which is x to the fourth, plus 2x squared dx. Okay, so let's simplify that. We get 2 pi. It's going to be 2x. Let's do this in decreasing order of power. Minus x to the fifth, and then we'll have plus 2x to the fourth. And then we'll have what else? 4x squared. And then we'll have, let's do the cubic power first. Actually, the cubic one is going to be minus 2x to the third, and then the second power one is plus 4x to the second. Okay, so I'm just foiling that out and putting it in decreasing order of power. Make sure I did that right. So that's, yeah, I think that's good. Okay, so the last thing to do here is just to evaluate that integral. So we get 2 pi antiderivatives all the way around. We're going to have minus 1/6 x to the sixth plus 2/5 x to the fifth minus 1/2 x to the fourth, and then plus 4/3 x to the third. And it seems like all of these have the 0 and the 1, which is kind of nice. So plugging in 1, negative 1/6, plus 2/5, minus 1/2, plus 4/3. Plugging in 0 again doesn't give us anything, just 0, so I'm going to put this into the calculator. 16, and multiply that by 2. 32 pi over 15 is what I get. 32 pi over 15. Okay, any questions about that one? Again, this is a good example because it shows us a situation where p of x is not simply x, and also a situation where h of x is not simply the function itself. So got to be aware of these possibilities. In general, if you're just revolving it around the x-axis, if you're just revolving it around the y-axis, p of x is just going to be x. if the function, if you're bounding by a function above and then just the x-axis below, then h of x is just going to be the function itself. But in this case, the lower bound of that rectangle is not the x-axis, right? And we're also not revolving it around the y-axis. And again, keep in mind that these methods can be used around for functions that are defined in that other way, right? For example, suppose I had a function x equals f of y, and I was revolving that around the x-axis. Well, then I could use the shell method on that, and I would have horizontal rectangles. In fact, in general, what I'll just try to give you some stuff to work with on this. For the washer and the disk method, the disk and the washer methods, the representative rectangles parallel to the axis of rotation. No, wait, perpendicular. It's perpendicular to the axis of rotation. In other words, if you are, so just for example, suppose you had something like this, and you're revolving it around the x-axis, right? Doing that kind of thing. See how the axis of rotation is horizontal, right? There's the horizontal axis of rotation. And then look at the representative rectangle. It's vertical, right? So axis of rotation horizontal, rectangle vertical. That's for the disk and washer method. Always going to happen with that perpendicular axis one way, rectangle the other, perpendicular to it. For the shell method, they are parallel to each other. The representative rectangle and the axis of rotation are parallel. And so you can see that that would work for functions that are, in fact, up here. Suppose we took this the other way, and suppose we had a function defined in the other way, like maybe a function like this, and we're revolving it around the y-axis, right? So revolving that region maybe around the y-axis. Then we would be using horizontal rectangles, right? And those rectangles, again, rectangle this way, axis this way, perpendicular, right? For the shell method, what you have, suppose I take this function maybe like this, and now I'm trying to revolve that function around a vertical axis, like the y-axis. Now you can see if this is my representative rectangle, it's vertical, right? Their rectangle is vertical. Axis is also vertical, right? So they're parallel to each other. Alternatively, you could also have a function defined in the other way. So perhaps this would be like a y equals f of x situation. This would be an x equals g of y situation. Same up here, the other ones I just did. Now, if you're revolving this, say, around the x-axis, so suppose I were to take this region, revolve it around the x-axis, right? And I wanted to use the shell method, I would use horizontal rectangles like that. And now rectangle is horizontal, axis of rotation also horizontal. So keep that in mind. It might help to decide, which method maybe is more appropriate.